Hello, this is Miss Lim again. Welcome back to the second part of magnetism. Okay, in this video, we'll be covering about demagnetization. Okay, what are some of the methods for demagnetizations, as well as some of the properties of your soft magnetic material, which is iron, and hard magnetic material, which is steel. Okay, let's move on. Okay, so over here you have a comic strip. There is this little boy who says that, why does the magnet keep dropping? Can we make it strong again? So then there's three parents over here who have different ideas. So the guy over here was saying, all the magnetism has been lost over time. I don't think you can make a magnet stronger. And then the girl over here says the magnetism gets transferred every time it attracts a magnetic object. Yes, I think you can't make it stronger. And then the lady over here in yellow says, can we stroke it with a stronger magnet to make it stronger? Okay, so you may think about such ideas. Why is it that objects with magnetism or a magnet will eventually lose its magnetism? Okay, so let's go into it now. Okay, so demagnetization. The process of demagnetization can be achieved through a few methods. Okay, the first method could be placing the magnet in the east-west direction and by heating like or hammering it, or by heating the magnet. Okay, by heating, it doesn't usually, we don't really heat magnets, but we tend to drop magnets. Okay, the more times you drop a magnet, the more likely the magnet will lose its magnetism faster. So why do we need to place it in the east-west direction? Because if it is placed in the north-south direction, there is the Earth magnetic field that will interact with it. Okay, the Earth magnetic field might still retain some of the magnet's property. So whenever we want to demagnetize a magnet, we usually place them in the east-west direction to minimize the influence of the Earth magnetic field during the demagnetization process. Okay, so this is what I mentioned. If you drop it multiple times in the hard surface, it's also going to cause the magnet to lose its magnetism. Okay, but we seldom use this method of demagnetization. The more appropriate way for demagnetization, and is the immediate method of demagnetization, is to again use electricity. We use electricity to magnetize it, or for induced magnetism. We can also use electricity for demagnetization. But for demagnetization, it's the same setup, just that we are going to use it with an alternating current. An alternating current is a current that changes its direction all the time. So within a few seconds or 1 second, it changed don't know how many times. Okay, so what happens is, this is what we do. We place the magnet that we want to demagnetize inside the solenoid, again in the east-west direction, and then we either slowly remove the magnet out of the solenoid, or we gradually reduce the current, the alternating current in the solenoid, until it becomes zero. Okay, it's the same meaning. So we are gradually reducing the magnetic field until it becomes zero, either by pulling it away from the solenoid or by reducing the current to zero. Okay, so this is how it works. Okay, so I have the same setup. Okay, but take note, now it's not a battery. Now it's an alternating current. So the alternating current symbol, it looks like this. So I have alternating current passing through this solenoid. So what does an alternating current do? It means that at one point of time, when the current is flowing in one direction, I have a north pole at one end and a south pole at the other end. But the next instant, when the current flows in the opposite direction, then my poles or my magnetic field over in this solenoid changes. So just now it's north at the left, right at for the right side is a south pole, but then now when the current changes in the opposite direction, it will be south at the left and north at the right. Okay, so the magnetic field keeps changing, left, right, left, right, left, right, north pole, south pole, then south, north, south, north. Okay, it keeps changing. Okay, And eventually, if you reduce it to zero, or you pull with the alternating current still flowing, so the magnetic field still keeps changing, you pull the magnet out of the solenoid slowly until it's far away from the solenoid. This magnet will no longer know what poles am I having, because the poles keeps changing. Okay, a while I'm north, a while I'm south, a while I'm north, a while I'm south. Okay, and eventually, if you pull it far enough, there will be no magnetic poles left anymore. So once there is no magnetic poles left anymore, we say that the magnet has been demagnetized. Okay, so over here, choose from the options below. You have options A, B, C, D. Stroke it with a magnet, heat and hammer it, wrap the solenoid around it, pass direct current, or redraw it in the east-west direction from a solenoid with an alternating current. What is the best way to magnetize an iron bar? And what is the best way to demagnetize a magnet? Okay, to magnetize iron bar, the best way, the strongest way, you can even control the strength of the iron bar or the strength of the magnetism you want it to have, is to use a direct current. Okay, is C. Wrap it around a solenoid and pass direct current through it. And the best way to demagnetize immediately is not by heating or hammering, it's by using a alternating current. Okay, same setup, but removing the magnet slowly in the east-west direction from the solenoid with an alternating current. Okay, next. Okay, so we know that under the influence of the Earth magnetic field and under the influence of heat or dropping, okay, magnets will eventually lose its magnetism. So to prevent this from happening, or we want to slow down the rate of magnets being demagnetized, we can actually make use of iron keepers. What are iron keepers? They are just iron bars. Okay, so this is the proper way of how do we store magnets. So I have two magnets over here, and these are the iron keepers. Okay, you will see that when I place the iron close to the magnet, I will induce opposite poles to it, induce magnetism. So this side I'll be induced with a south pole, this side I'll be induced with a north pole, and then similarly for the bottom. Okay, these induced poles will actually keep the magnetic field within this four piece of material. Okay, between these two magnet and these two iron keepers. Okay, so the magnetic field is like this. You will learn about the magnetic field in the third section of this chapter. Okay, so this will help to prevent it from losing its magnetic effect and from the nearby, and it will only be attracted to this iron bar. It will not be attracted to any other, this permanent magnet will not be attracted to any other things nearby. Okay, so it helps to reduce influence of the nearby magnetic field. Okay, so the magnetic field is retained within the iron keepers, and it prevents unwanted magnetized materials from being attracted to the store magnet. Okay, the magnet will only attract the iron keepers, it will not attract any other things. So a magnet that is subjected to the influence of external magnetic field and temperature variation may lose its magnetism gradually. Okay, but there are still many factors such as the warm temperature, or you might still drop it. Okay, so eventually all magnets will eventually lose its magnetism gradually. Okay, next we move on into the difference between soft iron and hard steel. Okay, iron and steel are both magnetic materials, but they are slightly different in their properties, and therefore they are used in different types of magnets. Okay, so there are temporary magnets and permanent magnets that we use in our daily life. So for temporary magnets, they are magnets that will only retain their magnetism for a short period of time. So for example, only when I have electric current flowing through me, then I will be a magnet. Or when I have a permanent magnet nearby, okay, or I place it in a permanent magnetic field, then I will have magnetism. But once I remove the current or I remove the magnetic field, then I will lose my magnetism. So these are only temporary magnets. Permanent magnets, on the other hand, they are they will retain their magnetism. Okay, they do not require any electric current or magnetic field nearby it. It itself has magnetism and it will always retain its magnetism. Not always, okay, because eventually it will lose its magnetism, but it will be able to hold on to its magnetism for a long period of time. Okay, so whether a magnet is temporary or permanent depends very much on the material that they are made up of. Okay, whether they are made up of something we call a soft magnetic material or a hard magnetic material. Okay, so this keyword of soft and hard magnetic material must be present in your answers. Okay, so a comparison of soft and hard magnetic materials, what are they? Okay, so magnetic materials, you learn there are 4 of them. I need complete science: iron, cobalt, nickel, steel. Okay, but in our syllabus, we will not focus on nickel and cobalt. We will only focus on iron and steel. So basically, just memorize iron and steel. Okay, you need to know iron belongs to the soft magnetic material, while steel belongs to the hard magnetic material. Okay, so what does soft and hard actually means? Soft magnetic material are materials that can be easily magnetized, but it can also be easily demagnetized. So I'm very easy to magnetize, but I also lose magnetism very easily. I'm used as a temporary magnet. For example, electromagnets. I pass current into it. I want it to be a magnet immediately. But once I stop my current, I want it to lose its magnetism, not become a magnet anymore immediately when I switch off my current. So it's easy magnetized, easily demagnetized, good for electromagnets, temporary magnets. Okay, but for hard magnetic materials, on the other hand, it's opposite. It's very difficult to magnetize. Then you take a long time. So if you were to put a steel into a solenoid carrying a direct current, it will take some time before the steel becomes magnetized, becomes an electromagnet. But it is also difficult to demagnetize. Means if I open the switch, it will still retain its magnetism. It will still have magnetic properties. It will not stop being a magnet. Okay, so usually for hard magnetic materials like steel, they are used to make permanent magnets. Like your compass needle, you don't want it to lose its magnetism. You want it to always have its magnetic effect. Your magnetic door catch in your fridge and in your daily home, okay, you have those doors with magnet knobs. Okay, you want it to be permanent. You don't want after a few tries, then it loses its magnetism. Okay, so we use steel, hard magnetic material. It takes a longer time to magnetize it, but it will retain the magnetism for a long period of time. So let's take a look over here. Okay, so I have a bar magnet. I'm going to induce magnetism in this iron and steel. Both iron and steel are magnetic materials, so I'm able to induce magnetism in it. Okay, so when I bring the North Pole close to the iron bar, this side will be induced and drop down. This side will be induced with a South Pole, and this side will be induced with North Pole. Similarly, South Pole, North Pole. You will see that for iron, there will be more paper clips attracted to it simply because it is more easily magnetized than steel. So iron becomes a stronger magnet immediately because it's easily magnetized. Okay, but the next case is if I were to remove away the magnet, okay, you will see that, let me just draw over here. If I were to remove this magnet and this magnet, you will see that for iron, most of the paper clips will have dropped. But for steel, most of the paper clip will still remain because iron will lose the magnetism easily once the magnet is being removed, but steel will still retain its magnetism. Okay, if you are interested in learning more about maglev train, okay, you may watch this video. This video makes use of a superconductor to illustrate how magnetic levitation trains works. Okay, but I'm not going to play the video over here. Okay, that's the end for the second part.